All right, so when we were talking about exothermic and endothermic reactions, we were concerned with the energy of the reactants and the energy of the products and the difference in that energy, right? But when we looked at the energy diagrams, that thing, right? When we were doing exothermic and endothermic, we cared about this difference, the difference between products and reactants. However, with all of the energy diagrams we saw, we also had this, what I'm going to call a hill, right? So I've actually denoted it as hill in here. There's this hill that exists between the reactants and products. And there's a reason for that, right? So what this simply means is that to get a reaction to start, not necessarily continue, but to get it to start, I need to put a certain amount of energy in. That's basically breaking the bonds, right? So I need to put some energy in to initially break the bonds, and then the bonds can reform, and that will release some energy. So during this process, when I start with reactants, that initial energy that I need to get from reactants to products, that hill I have to climb initially, is known as the activation energy, and it's capital E subscript capital A. So, when we think about reactions occur when, most of the time reactions occur when molecules collide with each other, right? So I got to get new things, new bonds have to break, new bonds have to form, and that means the atoms in the molecules have to collide and be close enough together to form new things, okay? That initial collision, however, a lot of the times is which provides enough energy to overcome that activation energy. Right? So, when we think about it, if a lot of collisions occur, and collisions occur all the time between molecules, but most of those collisions, unless we've got it set up, don't result in a reaction. Those collisions don't have enough energy. Things aren't oriented right, and they collide, but they go away the same molecules that they were before they collided. A lot of times, we're going to have to add energy to get those collisions to have enough energy, so we can overcome that initial activation energy, and we can let the reaction proceed. Okay, so to do this, a lot of times we simply heat things, right? We heat the reactants, they move faster, collisions are more violent and with more energy, and then reactions occur. All right. We can see in this case, we've got a pretty high activation energy, because the activation energy is the amount of energy from the reactants to the tip of that hill. Okay, that's the activation energy. That's the amount of energy I have to put in to get to for the reaction to go. Okay, in this case, in this energy diagram, we can see that delta H here is positive, meaning that the products have more energy than the reactants, potential energy than the reactants. So this is an endothermic reaction. Endothermic meaning not only do I have to put energy in to get the reaction to go, but I have to put energy in to get the reactants to the products, because the products have more energy than the reactants. Okay, and a lot of times we said that when we have that high activation energy, we'll increase temperatures of the reactants, and that will tend to provide enough energy for them to overcome that activation energy. Now, we should also talk about why there's an activation energy. If there wasn't an activation energy, then molecules would just fall apart, right? They would form together, and they don't need any energy to come back apart, so they would just come back apart. Okay, so, and some do, but the molecules that exist and are stable, they don't just fall apart. They need to have enough energy to collide with something and form a reaction. So that activation energy, that barrier, I'm going to call it, it's called a barrier, occurs so that the molecules don't just fall apart. All right. So the rate of a reaction, how fast the reaction progresses, how fast the reactants end up as products, is based a lot on how high that activation energy is. The higher the activation energy, the more energy we need to get from reactants to products, the slower the reaction is. So you can see on the right here, we've got a lower activation energy than the one on the left. Because of that, we would expect, if these are both at the same temperature, we would expect the lower activation energy reaction to happen at a higher rate and get done earlier, right? So they don't need as much energy. The reactants don't require as much energy to get over that hump. So we would expect that second one with the lower activation energy to occur faster at a higher rate.